Hello, everyone. Today I'll be presenting our work on federated design of compact and privacy-preserving deep neural network. My name is Farinaz Koushanfar. I'm a professor at UCSD, and this is joint work with my students, Mojan Javaripai and Mohammad Samra, as well as my colleague Tara Javidi, all at UCSD. There is no question that we see a lot of intelligence everywhere. In particular, we have a lot of data that is being gathered at the edge, and the AI algorithms have become much more complex. So the modern algorithms are both complex but much more accurate as well. And in order to achieve that high accuracy, we need to perform intensive computation, and in a lot of real-life situations, we need to do real-time execution. So this is basically becoming or forming the brain for the next industrial revolution, which is rightfully called automation revolution, where a lot of different devices are connected to a decision-making authority that is making decisions and automating a lot of things around us. Now, as you can see here, these data is being gathered from different devices and different platforms, and each of these platforms are providing a unique set of requirements and constraints. For example, if you're thinking about like a watch or a drone, there's a lot of the low power constraints. If you're talking about an automobile, there is a lot of constraints in terms of real time, because its decisions have to be made in real time. Otherwise, the system is going to fail, and so on and so forth. So the memory, the computation, and the power are really the resources that we have at our hands, that are the constraints of the device. But nevertheless, we want to map all these computing into these different platforms. And if we want to do this best computing and intelligence at the edge, taking advantage of all the capabilities that these devices have, we need to customize these models to the platform. And model customization to the various platform has been a very active research topic. This is something which is very often called AutoML, where we can do this automatically. If we can customize models automatically from a big model, fit it like and prune it, and make it fit a smaller device, but still with a similar level of accuracy. And it turns out that because of these models overestimation, we can very often remove some of the parameters and fit them and customize them well to the limits of the devices. There are a number of techniques that have been used in achieving this type of optimization. I'm just listing a few: pruning, decomposition into lower dimensional spaces, quantization of the levels of the inputs and the parameters, and so on and so forth. And this basically makes sure that we can achieve a certain accuracy while fitting a certain device. And a lot of research in AutoML has focused on one central device and doing this customization with one central device. Now, what we are really trying to do first in this project is trying to do federated AutoML. What does that mean? That means that, instead of one device now, we have a number of devices, but we still have the same goal. We want to maximally use the computing resources of these devices, and we want to be within the computational constraints of these devices. But there is one thing that is in our advantage, and that is these devices are really not computing sequentially, they're parallel. So in a sense, it feels like we have a server with parallel computing capability, and we want to just have this distributed system that optimizes the parameters in the best way while fitting the resources and constraints of each of these pertinent devices. Now, if you think about model customization, and here I'm just having a figure example of a deep neural network. What happens is that very often we try to understand, for example, with pruning, how many parameters we are going to have in each of the layer, and then in decomposition you're trying to have a mapping of these layers into lower dimensional spaces, and then look into the lower dimensional spaces and or tensors as it's named, to try to find the best number of parameters and the best number of components for each time. So if you want to customize this, using kind of a little bit more mathematical model, what we have is that let us assume that these decisions are made, and each of the layers, the parameters, we represent them in a vector. And now we have if we want to make this decision for the whole network, then we have one long vector which has all these computing, and then we try to optimize and make decisions for all these networks. The setting that we are talking about here is where the server has, holds this big model, and then every time it goes through a iteration with the distributed clients, it's going to send one of these vector sets that are specific to the client to that client, which is, and then the client is going to evaluate the objective function, or the goal function, or the cost of using this. And then the reward function comes back to the server, which makes a decision about what to send next in terms of the parameter vector to the next. So the scenario is that the server has access to a trained compute intensive and high accuracy DNN, but as we gather more data, we want to basically learn these new parameters and update the parameters, and based on this learn various example. And every time we want to send a compact version of the trained model to the client devices. The client devices have various requirements, and they have access to different data sample, and we want to optimize the CNN model to satisfy the client requirements. Really, the best design parameter vector X, which we showed earlier, that's the one we want to show, we want to optimize. So the formulation in a little bit more formal setting is really, having that cost function and trying to find the maximum of the cost function by, optimizing that decision vector. And the federated searches should be parallelizable. It should think about the aggregation of these parameters in a scalable way and to the number of clients. And we want to have lower or low hardware costs at each of the clients and a high accuracy. So every time we go to a client, what happens is that, we are going to send the hyperparameter decision vector specific to that client, and the client is going to evaluate the hardware cost and accuracy and give a score, and that score goes back to the server, and the server is going to compute that. Now, the main challenge in doing this optimization, which may actually look very simple at a high level, is really the fact that this optimization function that you're trying to optimize is not convex, it's not monotonic. There is a lot of interlayer correlation between this parameter vectors that I was showing earlier. The dimension of the problem is just huge. There is, if you think about the number of parameters, even for a resonant 110, we have about 10 to the power 132. And, the federated search is really what we are trying to design. We want to do a parallel efficient evaluation of samples on distributed clients, and we want to do it in an efficient way. We don't want to have exponential time complexity while achieving a good optimal solution, or close to optimal solution. Now, what we have as an algorithm here is really an adaptive sampling-based algorithm where, we have a pool of current samples with a current maximizer vector. And then the goal is to maximize the probability of finding a near optimal solution. So, if the optimal solution is F star, we want to get near to, near to that with that alpha max parameter, and we want to maximize the parameters for this. Every time we do this, we look into the score function or the reward function at this point and adaptively select the samples at this time t. We use them to choosing the samples at time t+1. And we basically are taking this random samples that are adaptively sampled, and then we use this to optimize the function in the best way. The advantages of this is that we can get a very scalable solution. We have shown that we can get to a lightweight and expensive solution because there is no need for backpropagation. Basically, once this reward functions or cost functions are sent back to the server is adaptively sampling all the decision vectors and sends the new decision vector to the clients. It achieves a linear speed up, and it's highly parallelizable. We have made this to be an end-to-end holistic and fully automated solutions, which reduces engineering costs and time to market. And the good thing is that it is directly incorporating the limits of the hardware or the constraints into the policy, and it's kind of really doing that federated AutoML that we were describing earlier. Here is just like a high-level overview again of this system. As you see here, the server is providing these vectors to the clients. The orange line shows the clients, and each of the clients takes this vector, translates it to the pruned or the reduced size network on its own, and then evaluates the cost, and the cost goes back to the server, which does adaptive sampling, and then after a few iterations, we really iterate to the best possible solution. Here, because of the time constraints, I'm just going to show a very small glimpse of the results. And if you're interested in the results, I'll be happy to talk about that. So the speed up in terms of finding a good solution is sometimes compared to the comparable solutions in AutoML, if we assume they're in federated setting, which is what our assumptions that I'm listing the work. You see that every time we did that, we had a good performance. We had this speed up in terms of the model. To up to 5 times speed up, and even up to 7 times speed up on the ImageNet. But the winning point has been really the time it takes to find the optimal solution. So for example, the search overhead for this solution, which is shown here, is 1 hour versus the overhead we had. One subject that is near and dear to my heart, because I do research in both privacy, security, and machine learning, is really how do we ensure privacy of the data and models in the federated learning setting. And if you think about privacy in general, there are various standard protocols. There is protocols based on differential privacy, which enjoy lower overhead, but of course you're trading off privacy with the overhead. There is the approaches based on secret sharing. There are approaches based on more crypto protocols, such as multi-party computation and homomorphic encryption. Now, each of these different protocols, they provide a number of advantages and disadvantages. And it turns out, if you're talking, and privacy by itself has to be well defined. So it turns out that the recent results suggest that the best solution in many settings is not like a single protocol solution, but a mix of these different protocols. So a subject that is really contemporary is how do you find the optimal combination of these protocols that ensure privacy of your machine learning. And privacy by itself could have different meanings. In particular, if you're talking about ensuring privacy of both the model and the data, we need to resort to more crypto-heavy solutions such as homomorphic encryption and multi-party computation, for example, the garbled circuit protocol. And, you know, this is something that we have observed, and I want to basically use this to also link it to the federated learning scenario that we just described, is that actually my group has the state of the art in provably secure, privacy preserving deep learning. We had a paper at User Security last year, which is considered the state of the art in this field. And what we did in that work is, in addition to optimizing the protocol in various ways, we also looked into AutoML. How do you customize these machine learning models to best fit the constraints of not just the devices, but also the constraints of the privacy protocol that we are dealing with. And this is the way we're going also with the federated learning privacy. We are thinking about all the challenges that are involved and all the constraints that are putting on the system. The challenges include scalability, the key management, if you're talking about the different keys, as well as timing, computing, communication overhead that we are trying to optimize. And really, we are thinking that the best solution to address and tackle this problem is having a mixed protocol optimization in addition to AutoML. So this is something that I think has a lot of promise for privacy preserving federated learning. In summary, we discussed adaptive search algorithm or federated search algorithm based on adaptive sampling called ADA-NS, which is paving the way for making federated AutoML. So we are making AutoML solutions in a federated way. It enjoys a linear speedup with parallel computing resources. Our preliminary results suggest scalability to search spaces as large as 10 to the power 100, and we have evaluated these on several different networks and data sets, and it turns out that the performance is better than many of the competing algorithms that are much more optimized heavy solutions. Our ongoing work is to apply this to heterogeneous devices and clients, non-IID data, and making the scalable privacy-preserving federated learning that I was just describing. With that, I thank you for your attention. I'd like to acknowledge the generous support of Qualcomm Innovation Fellowship, which supported my students for parts of this project. And if you have any questions, I'd be happy to answer.